Vibration analysis. Procedures for accurate evaluation of machinery condition. Special tests. Startup and coast down tests. This data is used to identify and verify imbalance, misalignment, resonance, and bent shafts. Startup and coast down data cannot be used in all cases because some machines will not coast when the power is removed. On other machines, the startup cannot be controlled. However, when a machine will coast where the startup can be controlled, these tests are valuable diagnostic tools. For best results, all startup and coast down data should be recorded because once the data is recorded, it can be processed as many times as necessary to obtain the desired results. If the data is processed live, you often have only one chance to take the data. If the equipment is not set up properly or other operator errors are made, this valuable data may be lost. An exact setup procedure cannot be established because there are several variables involved. However, the following information may be helpful. The real-time analyzer must have a peak hold averaging capability. With this averaging mode, every time the peak amplitude changes at any frequency, the amplitude is written to the screen. This procedure provides a maximum amplitude plot of speed as the machine starts up or coasts down. The frequency range should be just high enough to contain the maximum speed. Warning: the lower the frequency range used, the longer the real-time analyzer takes to collect data for one average. When the machine is increasing or decreasing in speed much faster than the averaging is performed, a smooth amplitude plot or curve cannot be obtained. In this case, the curve will have sharp increases and decreases, and the frequency range should be increased to reduce the time required for averaging. The number of lines of resolution can also be decreased to speed up the averaging. Sometimes it is necessary to both increase the frequency range and decrease the lines of resolution. The number of averages required depends on the real-time rate of the analyzer, frequency range, lines of resolution, and amount of time the machine will coast. For example, real-time rate is 10,000 Hz, lines of resolution is 400. Frequency range is 200 Hz, time required for startup or coast down is 3 minutes. Then, time to perform one average is 1 divided by 10,000 divided by 400 equal to 0.04 second. Time to collect data for one average is 1 divided by 200 divided by 400 equal to 2 second. Total time for one average is 2 second. Then, since 3 minutes multiply by 60 second per minute equal to 180 second. Then, the number of average equal to 180 divided by 2 equal to 90 averages. A total of 90 averages are required for the above given parameters. Startup and coast down data may require over 300 averages, depending on how long it takes to start up or coast down. As showing below. Figure 35, Figure 36, and Figure 37 in the previous video, Procedures for Accurate Evaluation Part 3, contain the imbalance frequency response curves for velocity, displacement, and acceleration. The amplitude at 60 Hz is 0.3 inch per second. The equivalent displacement is 1.59 mils, and the equivalent acceleration is 0.29 Gs. These curves were generated with the vibration calculator program. These curves provide the frequency response for a pure imbalance condition and are used to compare with actual coast down data to identify imbalance. These curves are also used to determine the increase in vibration associated with an increase in speed. The coast down data from a machine that has pure imbalance and is operating below first critical should resemble these curves. Coast down and startup data from a machine operating above first critical should resemble the curve in Figure 46. When power is removed, the amplitude decreases sharply by a small amount. This decrease in amplitude represents the loading factor. When the machine starts to coast, the amplitude follows the slope of an imbalance response curve. When the speed approaches the critical speed, the amplitude increases until the center frequency of the critical speed is reached. After the speed passes through the center frequency, the amplitude again decreases. The resulting bell-shaped curve is the envelope of the resonant frequency. By measuring the center frequency and the frequency at the half-power points, down 3 dB or 0.707 times peak, the amplification factor can be calculated as discussed in Chapter 1, earliest video talking about vibration analysis introduction. Coast down and startup data from a machine with misalignment should resemble the curve in Figure 47. This data can identify misalignment between the bearing center lines in solo data, and misalignment between the coupling halves on operating machines. When the power is removed, the amplitude drops sharply by a slight amount. This drop also represents the load. The amplitude then remains relatively constant or flat for a specific decrease in speed. The length of the flat line is determined by the amount of misalignment. The flat line indicating a given amount of misalignment can cause a problem in a given machine. Once the problem occurs, reasonable increases in speed may not cause an increase in amplitude. In other words, misalignment may be speed-related until the problem occurs and not speed-related after the problem occurs. In this coast-down data, calculate the amplitude at the half-power point, 0.707 times the average peak of the shelf or flat line. For example, 0.707 times 0.55 equal to 0.39. Next, identify the frequency at the half-power point, 43 Hz in this case. Then measure the amount of misalignment between the coupling halves, 0.015 inch in this case. This data indicates that this machine could be operated at 43 Hz or 2580 RPM with 0.015 inch misalignment. Several measurements such as this could reveal realistic alignment standards. When a machine is operating above first critical and the shaft is bent, the coast-down data could be similar to the data in Figure 48. This data indicates that the bent shaft is not causing a misalignment problem. When the machine has a bent shaft and is operating above first critical, a distinctive dip should occur in the bell curve representing the critical speed. The reason the dip occurs is because the phase of the imbalance shifts 180 degrees each time the machine goes through a critical. The bend in the shaft stays at the same place, and when the imbalance shifts 180 degrees, the imbalance must be out of phase with the bend in the shaft for a very short period of time. When this occurs, the machine tries to balance itself, and the amplitude drops. Since the phase shift occurs very fast, the imbalance returns as the coast down continues. Analysis is complicated when both misalignment and a bent shaft are present. The data in Figure 49 was taken from the center bearing on a 3-bearing turbine generator set. The shelf or flat line indicating misalignment is present. The distinctive dip in the critical speed envelope indicates a bent shaft. When this occurs, the questions that often arise are, is the misalignment causing a bow in the rotor, or is the bow in the rotor causing the misalignment? In either case, the machine must be removed from service, physical measurements must be made, and the necessary repairs must be accomplished. Thank you.